At 0247 local time, a Russian patrol boat watches its radar scope draw an impossible picture. Tiny contacts drift straight toward the most protected airspace over Crimea, moving too slowly for cruise missiles and too low for conventional aircraft. For the watch officer on duty, it looks like a software glitch. For one Ukrainian engineer hundreds of kilometers away, it is the moment a long calculation meets reality. Months of simulations, field tests, and arguments inside windowless rooms have led to this exact frame on that Russian screen. If he is wrong, the drones will die in seconds. If he is right, one of Russia's most valuable radars is about to vanish. On another monitor, far from the Black Sea, that engineer watches a different kind of display, a calm grid of telemetry numbers and signal strengths. He is not a pilot, not a special forces operator, just a specialist in radio links and geometry. His idea had been dismissed as unrealistic more than once. Drones this small were supposed to be for short-range attacks, not strategic strikes hundreds of kilometers deep into heavily defended territory. Yet the evidence on his screen says the system is working. The drones are flying directly into the defensive bubble around Mount Petri, and Russian sensors are still behaving as if nothing serious is happening. The first Russian reaction comes from the shore. A Pantsir S-1 air defense vehicle swings its search radar toward the incoming group. This is not outdated equipment. It is a modern point defense system designed to intercept fast cruise missiles and precision-guided bombs. In theory, it should have no trouble destroying small, slow targets. Its crew has drilled for years against simulated threats. On paper, they have every advantage. In practice, their radar is about to meet a flight profile deliberately shaped to exploit a blind spot in the physics of Doppler processing. On the drone's thermal camera, the Pantsir's missile tubes flash white as the first salvo rises into the night sky. Each missile represents tens of thousands of dollars and countless hours of industrial work. They accelerate, roll, and curve into their intercept trajectories with mathematical precision. Yet as the smoke begins to clear, the drone's video feed shows something that contradicts all of that training. No airburst, no shockwave, no fragments ripping through its frame. The drone is still flying, its electric motor humming steadily, its course unchanged. The missiles have flown past empty air. The Russian operator has just encountered a term that, until now, lived only in his radar manuals: the Doppler notch. Radar does not simply detect objects. It measures how fast they are moving toward or away from the antenna, a quantity called radial velocity. Moving targets produce a shift in frequency that allows computers to separate them from the static reflections of terrain and buildings. When a drone flies sideways across the radar beam at nearly constant distance, its radial velocity falls close to zero. To the software, it suddenly looks indistinguishable from the sea surface and shoreline behind it. To avoid being overwhelmed by false alarms, modern radars filter out returns that appear stationary. Ground clutter, wave crests, harbor infrastructure, all of this is suppressed so that missiles do not waste shots on meaningless echoes. The Ukrainian engineer has built his entire plan on that single design choice. By holding the drones at a very specific altitude above the water and forcing them to cross the radar beam at nearly a right angle, he keeps their apparent radial velocity barely above the threshold at which the filter begins to erase them. The Pantsir's radar is functioning exactly as intended, but its logic is being used against it. As if that were not enough, the sea itself is assisting. Each drone's radar reflection does not come from a single point. Waves scatter the signal and create a mirror image below the real target. The tracking computer attempts to average these two returns into one stable path, placing its predicted intercept point in the empty space between the drone and its reflection. The proximity fuse on the missile expects a radar echo roughly the size of a car door to trigger reliably. These first-person view drones present a radar cross-section orders of magnitude smaller. The missiles pass between reality and its reflection without ever entering the tiny volume of space where their fuses would decide to detonate. On the Russian side, radio traffic becomes tense. One voice reports multiple contacts that cannot be engaged. Another demands confirmation. Someone mentions missiles that refuse to hold lock. The system was designed and tested against high-speed threats approaching at hundreds of meters per second. Here, the closing speed is closer to highway traffic, and that seemingly trivial difference has rearranged the entire engagement geometry. 12 seconds from detection to flyby is not enough for a crew trained to sort, classify, assign, and fire at targets that behave like the manuals expect. The simple fact that these drones are too slow and too small is making them functionally invisible. From the engineer's perspective, however, the timing is not accidental. In the planning phase, he had rewritten the mission profiles again and again until the numbers aligned. Detection ranges, arming distances, fuse thresholds, all had been assembled into a single corridor in space and time where Russian defenses would be present but unable to respond effectively. To the operators on the ground, it appears as chaos. To him, it looks like a carefully sculpted gap. Holding the drones at a fixed height above the water while they cross each radar beam ensures that, for a brief but critical interval, every defensive algorithm is solving the wrong problem. The next move from the Russian side is predictable. If ground-based systems are struggling, call in a fighter. A Su-30 descends through the pre-dawn haze, its twin engines leaving a faint trail across the sky. On paper, this aircraft is a symbol of modern Russian aerospace power, roughly comparable to legacy heavy fighters in Western inventories. Its BARS radar promises long-range detection against small targets, and its missile load includes weapons designed to engage agile aircraft in close maneuvering combat. None of those design briefs imagined a sky filled with hobby-grade airframes, barely larger than seagulls. As the fighter approaches the area, its radar begins to show specks that refuse to behave like normal tracks. For one sweep, they appear. On the next, they faintly smear into the general noise pattern and vanish. The radar software demands multiple consistent returns in a row before it will call something a solid target. The drones never provide that. Their tiny radar signatures wander up and down near the noise floor, the natural background of radio reflection and interference that every sensor must ignore to remain usable. Each time the computer almost believes in them, their signal strength dips and the algorithm resets its confidence back to zero. The pilot, watching these erratic marks blink on and off, has to decide whether to trust the system or his instincts. Training tells him to wait for a firm track before committing weapons. The situation on the radio says there is no time. He chooses to fire. An air-to-air missile drops from a wing rail, its motor igniting and driving it forward faster than any drone can possibly move. Its infrared seeker searches for the bright plume of a jet engine. Instead, it finds only the faint warmth of small electric motors and batteries, hardly more distinct than the ambient air. By the time the seeker finally senses that slight contrast, it is already too close and moving too quickly to curve sharply enough. The missile flashes past, its fuse never seeing a convincing target. A second missile follows, then a third. Each one is a masterpiece of engineering, guided by control laws refined over decades. They are designed to outturn fighter pilots pulling extreme G-loads in high-altitude engagements. Down here, at low altitude against slow targets that make jittery micro-corrections every few seconds, those same control laws become a liability. The missiles are always solving the last position, not the current one. By the time they have rotated their control fins and adjusted their flight path, the drone has shifted just far enough that the blast passes to one side. The thermal cameras on the drones capture each near miss as a wash of white that fills the frame, followed by the steady return of the horizon. Frustration grows in the cockpit. There is one weapon left that does not depend on complicated seekers or fragile lock conditions. The pilot selects the internal cannon. The fire control computer calculates the range, speed, and heading, then generates a perfect lead solution for a target that continues in a straight line. That is the assumption baked into the model. The drones, however, are following a different script. On the engineer's orders, their guidance software injects tiny random offsets every few seconds, lateral shifts of only a few meters at a time. Over the distance, a shell must travel. Those minor deviations translate into misses wider than entire vehicles. Shells tear through the air where the drones were supposed to be, not where they actually are. While the fighter expends ammunition, one of the lead drones from the first wave reaches its assigned objective. On the plateau near Mount Petri, a 96 L6E radar sits on its vehicle mount, its distinctive array oriented toward the horizon. This system feeds targeting data to long-range surface-to-air missile batteries, acting as an essential sensor for the broader network. Without it, those much publicized systems can still launch, but their effective reach collapses to the narrow slice of sky their organic radars can see. The engineers selected this antenna for a reason. It represents not just hardware, but the connective tissue that turns individual batteries into a layered shield. The drone's flight controller executes the final dive without human corrections. Its shaped charge warhead is designed not to blast outward in all directions, but to focus energy into a narrow jet of metal, traveling at several kilometers per second. When that jet strikes the array, it does more than puncture metal sheets. It digs through waveguides, power distribution paths, and sensitive receiver modules, creating conductive channels between circuits that were never meant to touch. In a fraction of a second, high-frequency electronics that took years to manufacture become a maze of short circuits and molten fragments. From the engineer's point of view, a key node has just switched from active to permanently offline. The Su-30 climbs away, low on fuel and munitions, reporting an inability to defeat the threat. Below and ahead, more drones are still advancing. On Russian scopes, a new pattern begins to emerge that unsettles radar operators. Additional contacts are appearing on the coastal approaches, but they do not line up with expected routes from Ukrainian territory. Instead, they seem to materialize well out at sea, as if arising from the water itself. Displays in the regional command center repeat the same story, dots blooming inside a volume that the defensive plan treated as covered and safe. The more they examine the geometry, the less it makes sense according to their assumptions. The explanation sits on the surface of the Black Sea, riding slow swells far enough from shore to be out of visual range. Uncrewed boats belonging to a new Ukrainian class serve as floating relay stations. They carry antenna masts, satellite communications terminals, and racks of electronics rather than heavy weapons. The engineer had argued for this architecture early in the war. Directly piloting first-person view drones from a distant city is not feasible over such ranges. The curvature of the Earth, losses in the atmosphere, and line-of-sight limitations would kill any direct radio link after a relatively short distance. Relay platforms stationed partway to the target solve that without needing to be large or heavily defended. From his control room, the engineer's operators sit behind consoles that look like any other ground station. They connect to the relay boats via encrypted broadband links, often leveraging commercial satellite networks adapted for wartime use. Commands travel from the city to the boat, then from the boat to the drones, using high-gain antennas optimized for short-range reliability. Video feeds follow the same route back. To the person guiding a drone through a thermal image, it feels as if the aircraft is only a few kilometers away, even though the actual geography involves hundreds of kilometers and multiple network hops. Latency remains low enough for precise maneuvers because each leg of the journey is tuned for minimum delay. This system has additional advantages that the engineer had emphasized in his design brief. By placing the relay boats within a few tens of kilometers of Crimea, he turned them into local nodes that are hard to distinguish from ordinary maritime traffic. Coastal surveillance radars are usually configured to ignore slow-moving small vessels, treating them as non-threatening clutter. To reduce false alarms, filters suppress returns from anything below a certain speed. The Ukrainian boats intentionally stay under that threshold, mimicking fishing craft and service barges. When their signatures appear alongside dozens of legitimate civilian contacts, automated processes downgrade their priority. Human screens show them as just more noise on a crowded coast. At the same time, the main long-range radar on Mount Petri, a Podlet K1 system, faces an unavoidable constraint set by geometry. Its antenna sits high above sea level, with a mechanical limit on how far it can tilt downward. The combination of altitude and minimum depression angle carves a wedge-shaped blind zone close to the mountain, a region where low-altitude objects simply cannot be illuminated by its beam. Inside that zone, the only way to achieve coverage would be to add separate sensors at lower elevations. The engineer mapped this blind volume using public topographic data before the operation ever began. When he positions his relay boats within that invisible pocket, they become ghosts to the very radar meant to protect the peninsula. As the relay boats quietly hold position inside that blind pocket, their launch rails elevate and hum to life. Fresh drones rise from each deck like sparks lifting from a fire. They do not form neat formations or fly predictable arcs. Instead, they scatter outward along paths that look random to any observer. The less these paths resemble military attack patterns, the lower the chance of software triggers, assigning them higher threat levels. To Russian algorithms, the swarm looks unstructured, weak, and unworthy of urgent response until it is too late. One of the incoming drones closes on the first of the protective domes near the summit. These fiberglass shells were engineered to withstand heavy bombardment from above. Designers calculated blast overpressures, fragmentation patterns, and shockwave dynamics, ensuring the radars within could survive near misses from powerful bombs. The engineer had noticed maintenance access points built at the base of several domes, each sealed with reinforced steel, but never intended to stop a focused jet of metal driven at extreme velocity. The drone's onboard camera captures the final meters before impact. Barriers that could shrug off large bombs become irrelevant inside the dome, delicate components that require precise alignment. A radar designed to detect objects hundreds of kilometers away becomes incapable of sensing objects even a few meters distant. Simultaneously, another drone reaches the Nebo radar, a meter wave system valued for its ability to track targets that evade traditional bands. The shaped charge from this drone enters at an angle that intersects its power distribution lines and critical switching modules. When the copper jet carves through insulating materials, it creates conductive channels where none should exist. With these major sensors eliminated, the integrated air defense network loses the pieces that allow long-range coordination. Without the low-altitude coverage from Podlet K1, the terrain-hugging drones vanish behind Earth curvature. Without the 96 L6E dish, handoffs between batteries become impossible. Each system is now an isolated island, seeing only what is directly in front of it. Farther downslope, a BK-16 landing craft attempts to intervene. Its crew has spotted the swarm visually and through its navigation radar. The crew cycles through every weapon they have, from heavy machine guns to small arms, saturating the air ahead with rounds. Yet the drones, guided by precise position references and flying low enough to blend with thermal noise, navigation radars can paint dots. They cannot lead targets, drifting laterally at unpredictable intervals. On the mountaintop, the final stage unfolds. A drone aimed at the Ipetri command post descends into the reinforced entrance corridor. This bunker directs data flow for the entire western Crimean air defense structure. When the door crumples under the shaped charge impact, the blast wave travels down the confined passageway with amplified force. Cables rupture, processors shatter, and internal components ignite. Fire spreads rapidly through bundles of wiring, insulated with materials never intended to withstand direct heat. Secondary detonations follow as small stores of ammunition and reserve fuel ignite. The engineer watching from afar sees the telemetry collapse in sequence. First one radar, then another, then the primary command node. Bits of data that mark them as active change state or disappear entirely. Each sensor falls within a few minutes of the others, creating a cascading blind spot across the entire region. The remaining Russian batteries continue scanning, but they have nothing to guide them. No shared tracks to follow, no coordination to support a response. Smoke rises from the summit as the final drones strike their targets. With the radars offline, the defense grid cannot reacquire anything approaching at low altitude. The strike did not succeed because the drones were particularly advanced or because Russia's equipment was inherently flawed. It succeeded because the geometry of the battlefield, the thresholds in radar design, and the predictable filtering behavior of modern air defense systems created narrow windows of opportunity. When the last transmitter on the mountaintop goes silent, the operation reaches its end. A network once advertised as impenetrable now struggles to sense anything beyond its immediate line of sight. The gap the engineer constructed is no longer theoretical. It is carved into the radar picture itself. avoid where detection should have been. In that space, hundreds of millions of dollars of equipment have failed to stop aircraft built from off-the-shelf components and guided by calculations that began as sketches on a workshop board. This outcome reshapes assumptions across the region, marking a moment when a single idea, applied with precision, altered the reach and stability of an entire defensive system.